Dilogarithm is helpful in such cases. Okay, but let's see how. And this is also pretty interesting because the sum of harmonic numbers is actually equals to Riemann zeta of 2 by 2. Yeah, that seems pretty an interesting result, and let's see how we prove that. So this is basically the generalized. I mean, this has generalized sum expression. Basically, as n by n x to the power n, and then we will substitute x as 1 by 2. Yeah, that will do our work. Now for that, I'm going to take directly going to take help of the other sum expression, which I have already proved in one of my videos. You can find it in the playlist of classical Euler sums in my channel. Yeah, or I will also keep this video in description. Yeah. Now I have proved in one of my videos that this is actually equals to, let's say if it's of order p, then that is equals to LIP of x by 1 minus x. Yeah. And now what does this mean is Hn to the order of p means that sum going from k equals to 1, sorry, n of 1 by k to the power p. This is what it means. And when p is equals to 1, we just have the nth harmonic number, and the Li1 of x is minus ln of 1 minus x by 1 minus x. Okay. Now we use this tool sheet, and proof is on my own channel, or I will also link over here. Yeah, fine. Now using this, what we can do is we can basically divide by x and then integrate this result to get the other expression. Basically, if we divide by x, what do we get? From n equals to 1 to infinity, hn x to the power n minus 1 over here, and over here we get minus ln of 1 minus x by x 1 minus x. Yeah. Now if we integrate both of them from, let's say, 0 to t, also this one from 0 to t dt. Over here we get the required expression now. This will just be sum from n equals to 1 to infinity as n x to the power n by n, yeah, from 0 to t. And over here is the thing that we need to find out. Yeah. And note that we can break this into partial fractions. Basically 1 by x plus 1 by 1 minus x. This is not dt actually, this is actually dx. I'm sorry. dx, dx, dx. Yeah. Now this one is now sum from n equals to 1 to infinity hn by n of t to the power n, and then minus 0, so that doesn't matter, let's not write that. And now this can be broken down into two expressions, minus ln of 1 minus x by x minus ln of 1 minus x by 1 minus x dx. Now to integrate this is not too hard, because this one is just the definition of Li2 function. Yeah. And over here, if you take ln 1 minus x as y, minus 1 by 1 minus x dx will just be dy. So that's why the answer will be ln square 1 minus x by 2. That's y square by 2 basically. Yeah, and this is from 0 to t. Okay. I shouldn't really have it done here t. Let's write it. Okay, and okay, then just let's use the limit for this one only. Yeah, the other one is already done. Li2 of t plus, now for this we have ln square 1 minus t by 2, and then ln square 1 is 0. So this is the answer for this sum from n equals to 1 to infinity hn by n of t to the power n. Now if you want to substitute t as 1 by 2, isn't it? 1 by 2 to the power n. If we substitute t, as 1 by 2. What do we get? We get Li2 of 1 by 2 plus 1 by 2 ln square 1 by 2. Yeah. Now how do we find Li2 of 1 by 2? So we basically now use Euler's reflection formula of polar logarithms, which states that Li2 of x plus Li2 of 1 minus x, this is equals to Riemann zeta of 2 minus ln of x ln of 1 minus x. Using this, if we substitute x as 1 by 2, we get 2 times Li2 of 1 by 2 is equals to Riemann zeta of 2 minus ln square 1 by 2. Yeah, and now we can take 2 to other side. That gives us Li2 of 1 by 2 is equals to Riemann zeta of 2 by 2 minus ln square 1 by 2 by 2. You see, now if we substitute that, we get Riemann zeta of 2 by 2 minus ln square 1 by 2 by 2 plus ln square 1 by 2 by 2. This to cancel out, and that gives us the answer as Riemann zeta 2 by 2. This can also be written as, this is pi square by 6, so pi square by 12. And see how interestingly this harmonic sum comes out to be in terms of pi square by 2. And isn't that awesome? That is. Now let's talk about the flow. We use this general formula, or let's say identity. We divided by x and integrated. And we had to do some works to find the integral of the other one, and then we placed the values and got the answer. That was it. Hope you enjoyed the video. Thanks for watching and look forward to seeing the upcoming videos too.